when my wife and I were young, there was a tragic accident in our community where the baby was left in the car in the summer. I think it was about 45 minutes because I was there in the vicinity. It was remembered that the baby was in the car, got the baby out of the car and inside, and I gave it CPR and it was foaming at the mouth. Actually, I don't think I did give it CPR because it was breathing still at that point. I say it, but it was foaming at the mouth. Went to the hospital, died a week or so later. This is what happens to babies and or say grandparents. Grandparents. And so old people can't regulate their body temperatures very well. Small bodies like babies can't. One more story. When our son was about 6 weeks old, we were in Memphis visiting his grandmother, and all of a sudden he was spiking 105-degree temperature. Took him to the ER, and they did like a spinal tap to check for spinal meningitis, but at the end of the day, it was just a really, really bad ear infection. So when you're parents, these ear infections can send these temperatures up, but yeah, they put him in a water bath for that. All right, so we've got all these right now as we sit here. We have all of these thousands of chemical reactions going on in our bodies. And if it weren't for the fact of things called enzymes, everyone knows about enzymes. Enzymes are biological catalysts, and so what they do is maybe the chemical reaction would normally take place at 250 degrees Fahrenheit. They're going to get this thing down to lower than 106, somewhere below 106. So some optimal range of operation probably in the 90 degrees, in the 90s. So enzymes are biological catalysts. And I'm looking for my coffee over here. Enzymes are biological catalysts that allow our bodies to function at something less than the temperature which we will cook. All right, one second here. All right, in chemistry though, they are critical for chemical reactions. All right, word equations. We do equations in one of two styles, either with the chemical symbols being used, and that's 99% of the time. No one wants to write all this stuff out. But I would read this as iron plus oxygen yields iron 3 oxide, or hydrogen peroxide yields water and oxygen. Methane and oxygen yields carbon dioxide and water. Now this is our chemical reaction that we're used to seeing, and so we've got iron, that's the same reaction. Solid iron plus gaseous oxygen makes solid iron oxide, or peroxide, aqueous peroxide, plus a catalyst, hello, manganese oxide again, yields water plus oxygen, liquid and gas. So that's the more common way. That's the almost 99% of the time we're going to see it like that. All right, the big 6 chemical reactions. This is what you're going to be working with on your project. Oh, sorry. All right, thank you. All right, these are the big 6. You must be comfortable with all 6 of them tomorrow you will be searching for and describing 2 types of each of these in your PowerPoints. And I'll save a couple minutes here at the end to talk about that PowerPoint. So, synthesis, making something out of stuff. Decomposition, breaking something down into stuff. Single, double replacement. Neutralization, where we neutralize an acid or a base and bring it up to a pH of 7 or down to a pH of 7. And then combustion, our ever favorite combustion reaction. All right, here's your synthesis reaction. And these are shown as the actual molecules. So here you have your diatomic hydrogen, and you have 2 moles of that. So this is a balanced equation, which is chapter 12. 2 moles of that plus 1 mole of oxygen. Again, diatomic, that's the only way you're going to breathe it or use it as a naked element in these reactions. And yielding 2 moles, 2 moles of water, 1, 2. So we take 2 things and we bring them together to make a unique product. And what you'll want to do tomorrow and Wednesday is, as you read about reactions, you'll be describing what happens, what the conditions are, writing a paragraph about it, and then you'll be looking for that reaction in Google Images. You'll find that downloaded, inserted into the PowerPoint. So that's kind of the path this is taking. All right, so synthesis reaction. When we make magnesium oxide, magnesium plus oxygen, magnesium oxide, that will be a synthesis reaction. That one's pretty easy. Decomposition, we're going to break something down. Decomposition breaks something down. And when you are looking for that, on Thursday we will do a worksheet. Thursday we'll be doing a worksheet where you will be identifying these 6 different types. By Thursday it should be old hat because you've worked on the PowerPoint. You take something, you take a single compound, and then you do something to it, something happens to break them down into 2 or more components. Doesn't have to be just 2, could be 3. And so here we have down here potassium chlorate makes potassium chloride and oxygen. Calcium carbonate, you get a precipitate, you get a solid calcium oxide and CO2 gas out of that. So those are examples of decompositions. All right, the replacements, the double and single replacements are where they get complicated. All right, we start out with 2 reactants. We have a simple reactant and we have a compound. And what happens is some switching takes place. The B and the C gets split up and they recombine as AC. A started out alone and then connected with whatever C was. And so one of the favorite examples of that is like going to the dance, going to the homecoming dance next week. And so you've got switching dance partners there. That's a good way to think of that. And so when you're looking for that in a problem situation or a test situation, you're looking for this to get broken up, the more complicated compound, and then whatever this species was, whatever element it was, then partnering up with it. So that's a single replacement. I'm going to move out of the way so that Matthew can make whatever marks he wants on that. Give Matthew a minute. Single replacement is pretty easy to determine. Its friend, double replacement, is a bit trickier. Let me erase the board. Double replacement is often harder to see. Often harder to see. It's the toughest one to pull out of a problem. So we have two compounds. Sodium sulfide, hydrogen chloride. And so they're both compounds. If you have just an element, it can't do this. It's got to be two compounds. And in the reaction, they're going to be split. And recombined. Hydrogen comes over here. Chlorine now joins up with sodium. We know all about salt. Sodium is here. And the sulfide switches there. So again, we tend to struggle with this, identifying this reaction. But if you don't have two compounds in the beginning to be broken up into something simpler, it can't be. Can't be. All right, while you guys are drawing the arrows, I'll get out of your way. Green, join the living. Trickiest one to find. There. Jane, are you good? All right, neutralization reaction. And we talk about putting baking soda on acid, on something acidic in the lab. If we have an acid spill to neutralize it, that's what we are talking here. And here's several ways to view it. An